Hi everyone, and welcome to the second session of Digitodontics Webinar Series. This is Mahmoud Al-Bashti with you today from the Digitodontics International Academy. It's our pleasure and honor to welcome our guest speaker, Dr. Pravinkumar Patil from Kuala Lumpur, Malaysia. Dr. Patil will share with us his experience in finite element analysis as a smart implant research tool. Dr. Patil is a prosthodontist and implantologist, a senior lecturer and a program director of the postgraduate diploma of prosthodontics at the School of Dentistry, International Medical University, IMU. He is also an adjunct professor in prosthodontics at the D.Y. Patil Dental College, Beyond India, and VSPM Dental College, Nagpur, India. Dr. Patil is a faculty of examiner at the Royal College of Surgeons, Edinburgh. So far, he secured 22 research grants of $75,000. He has been an invited speaker at major conferences in South Korea, Malaysia, Sri Lanka, Myanmar, and India. Dr. Patil is a member of the editorial board of the Journal of Prosthetic Dentistry and the International Journal of Maxillofacial Prosthetics, and the Council on Prosthodontic Research. So just before Dr. Patil starts, I would like to mention that attendees can write down their questions in the Q&A section, and then after Dr. Patil finishes the webinar, he will answer your questions. So without any delay, let us welcome Dr. Patil to share with us his experience in the finite element analysis as a smart implant research tool. So Dr. Patil, I think the stage is yours, please.
Yep. Very good afternoon, good evening, and good morning to one and all. Thank you so much, Dr. Mohammed Al-Basti, for a wonderful opportunity to talk into the this wonderful international academy, which is known and it will be a famous soon, and it's already a famous and called the Digitodontics Webinar Series under DIA, Digitodontics International Academy. Thank you so much. Let me just share my screen now.
Yes, it looks very good. So
okay,
I think everything is good. So you can start.
Yep. Thank you so much, Dr. Mohammed, once again. So finite element analysis, a smart implant research tool. Let's have a journey to understand what exactly this means, and very close to my heart, especially this topic when we are thinking of stress and strain analysis of in dentistry, especially in implant dentistry, when you are thinking of that. Before I go to the slides, thank you so much once again, Dr. Mahmoud Al-Basti, for this wonderful opportunity. Yeah, a little bit of myself. My career journey in prosthodontics started way back in 2008 when I was graduated from prosthodontics in Government Dental College and Hospital Nagpur, and then later have a couple of exchange program in Japan, and then got a MFBS in Edinburgh and Glasgow, and then ITI fellow as well. I am associate editor-in-chief in International Journal of Prosthodontic and Restorative Dentistry, and editorial board of Journal of Prosthetic Dentistry, and adjunct professor for a few other colleges in India. And I'm currently working as a senior lecturer and program director in International Medical University for PG Prosthodontic diploma program. So I came from a vibrant city of Twin Towers, a capital city of Malaysia known as Kuala Lumpur, and in a western part of the Kuala Lumpur, we have an international medical university where we practice, we educate, we teach dentistry and postgrad courses in International Medical University here. Let's begin with and understand with the topic itself now. Finite element analysis is not really a new phenomena. It has been used in a lot of mechanical and especially when those are having a complex structures in society, when in engineering, especially in civil engineering and as well as in aeronautics and so on. So let's take an example of how this car has been crashed. Do you need to test the crash test for, especially for the cars or whatever physical models, every time when you want to do some changes in the design, every time you do some change in the materials, every time you need to do some of the material aspects changes and so on. So every time it is not possible. So that's basically the crux of this particular tool, which is a finite element analysis, where the engineering has discovered that the whole of this physical model will be converted into the small tiny elements which are of a triangle or of any other shape, and those will be given some properties of that particular material in terms of the mathematical calculations, and the whole of this software model will be created and simulated, I would say, to test any particular stresses or strains or whatever type of fracture tests and retention tests and so on. So when you look at a particular model of software model in this particular session, you can see now that you don't really require every time any physical thing to be tested. If you can manage to go very closely to the physical modeling by doing this finite element analysis and so on. So especially when you can see what do we mean by finite element method, and what is the difference between the finite element method and finite element analysis. Now, this is a very popular method for numerically solving the differential equations arising in engineering and mathematical modeling. A lot of times it is used to solve the complex problems by breaking it down into the smaller, tiny, more manageable pieces called elements. Those are finite elements. That's why it is called as. And studying this or analyzing this phenomena of method of finite element is often referred to as finite element analysis. Now, there are perspectives of different people who can be connected with this particular method. There are the engineers' point of view where they focus on particularly on practical modeling of and solving that problem. There is programmers' view where a finite element methods will be applied and how they can be easily been understandable for the person who is doing that simulation in terms of coding and automation. Mathematician will go too much of deep inside to solve these problems, and how these mathematical calculations will really help solving the real life scenarios, which are complex and which are very sometimes difficult to really test it in physical scenarios. And then the clinician's perspective, as long as we are in dental and dental implant dentistry is concerned, we also wanted to see without actually doing the physical testing or clinical testing, we would also like to simulate, we would also like to evaluate these types of stresses and strains patterns in terms of occlusion and the following the transfer of these stresses in all over the jaw and jaw movements. And so that's where the crux happens. So let's understand a simple example of, we are having a edentulous mandible. We want to put 4 implants and then 2 implants in the canine region probably, and then 2 more implants, posterior implants in the somewhere in the posterior premolar region. And what if we can just tilt 2 posterior implants backside and having a laser cantilever length, and that was a concept, yeah. And then so what? So if your patient is occluding on the denture with support of these 4 implants, where 2 implants are tilted on posterior side, and then what will happen to the distal most area of those 2 tilted distal implants, and whether by any of this logical person, if you apply some vertical forces to those tilted implants, and then there will be some definite degree of higher stresses around those distal elements or distal aspect of those tilted implants, and that's where you probably may expect some extra bone loss as compared with those implants which are parallel to each other. And that's where clinically you want to know. So if you want to know that you can go tilted implants, you cannot go tilted implants, you can how much degree of implants you can tilt for having a clinically favorable results, no bone loss or lesser bone loss. Every time you cannot go for putting those implants with different categories or different angulations and different types of implants and different positions of implants for every different patient and then evaluate is impossible and is technically not practical. And that's where the finite element analysis will help you in analyzing those stresses, whether we are really been coming on those areas where we are actually expecting that higher stresses will be developed. Way back in 2015, there was one wonderful article published on the all on four concept, where the clinician has smartly used this finite element method by changing different implant angulations for posterior implants and by changing different types of load in different areas, and evaluated whether changing the angulation, whether the changing the position, or whether the changing the amount of force virtually may affect the jawbone, may affect the implant itself, may affect the mucosa. And that's where the finite element analysis helps a lot. And look at the results of this particular study. They have tested with a 15 degree, 30 degree, and 45 degree of distal angulation, and there is a negligible difference between the 15 and 30 degree of models. However, 45 degree of models have indicated higher crestal bone loss or higher peri-implant stresses. Yeah, so increasing the tilt of or degree of the angulation of the distal implants will be increasing proportionately the stresses or stress concentration around the implants. And that's exactly what we also can hypothesize and evaluate the testing with the help of these models and so on. So finite element analysis is not new in dentistry. It can be used in a lot of jaw studies. It can be used in dental implants, can be used in a fixed prosthodontics, can be used in any of the using the cortical bone or medullary bone. It can be used in occlusion analysis. It can be used in implants with different models, different designs and surface topographies, and even it can be used in a post and core and so on. Okay, so when you look at the PubMed search, and I just key in the search term of finite element analysis in implants, and what number you got is a 640 results still from 1980 to 2022. And look at the graph, which is completely increasing on the verge of increasing in the number of finite element studies which are published overall. And that's exactly what is happening around, and that's exactly what is the amount of research is happening. When I looked at the systematic reviews, I could find not much because of the heterogeneity of a lot of studies. You cannot really correlate or simulate the similar types of finite element studies to take it to the systematic reviews. However, there is one systematic review in 2016 published with the 20 finite element studies, and which are actually indicated with the bone layers or types of bone or osseointegration level or design of the implants or diameter or length of the implants and so on and so forth. So there are multiple studies are happening around the implants, testing different aspects of the stresses, whether they are really helping clinically to come up to very closely with a less and less bone loss or less and less stress concentration around each and every component around the implants. And these are some of the details of the same study, where all these 20 studies have evaluated different types of implant, different diameters of implants. Then you can have different implant connections, abutment connections. You can see different loading protocols, and then you can see the oblique loading or vertical loading or lateral loading, and then you have evaluated the stress and stress analysis. So this is just a 5-year study where they have done the systematic review between 2011 to 2016. There is another systematic review published recently in in 2019, where they have also evaluated almost 16 studies comparing the 3D finite element analysis in the in implant dentistry. Okay, so there are a few couple of mechanical studies, and there are a couple of finite element studies which you can say have been tested. So when you look at different studies in edentulous mandible, you have a different types of processes possibilities, and when you look at the different possibilities of a different number of unsplinted 4 implants, or they're splinted 4 implants, or splinted 4 implants with a cantilever, or splinted 4 implants with a fixed restoration. So anything like a first 3 options of a removal options, or a fourth option of a fixed restoration option, and then every model has been simulated in finite element analysis method, and then evaluated subsequently to check how this stress concentration is happening, where exactly the stresses are concentrating, so that we can evaluate how we can predict the bone loss in which areas, and particular implant is really susceptible for extra stresses, whether, and that's how. So if you want to do everything clinically, it will take years together to evaluate the same thing, with to correlate whether the bone loss is happening around some specific implant, and we don't really know to specifically clinically or mechanically how far and how many samples required to really come to a conclusion, and that's where the finite element analysis is helping you out. Okay, so typically the process of finite element analysis goes like, you may go and design the structure with the help of softwares with the mechanical designing, or you can go with developing the anatomical models with the help of different softwares like mimic software. Once this 3D modeling is done, then these 3D models are converted into hyper mesh softwares using this meshwork to convert this 3D model of that particular structure into multiple millions of tiny nodes or elements, and these elements will be actually you can change the size and shape and whatever requirement. More the finer the elements, more number of elements will be requiring increasing the accuracy of the measurements and so on. So whole of this 3D structure is suddenly converted into a surface 3 meshwork first, and then the volumetric meshwork, and then the whole model, the mesh model, will go into the another analysis software for post processing, and then providing these actual stress and strain values, so that you can visualize how are the stresses distributed and concentrated all around. So process wise, when you really want to go and design the 3D model, and you want to simulate a whole of your jaw outside in the software computer, how to go about it? So you have a CT scan, CBCT, cone beam CBCT. Let's take an example of modeling of 3D modeling of mandible. So you take a CBCT of a particular patient which you intend to evaluate the stress analysis, and now you can go and create the 3D model of the mandible. So there are some multiple softwares will be coming into a picture in different stages of the process, where materialized mimic software is one of the very important and crucial software, where you can convert the CBCT DICOM images into the actual convertible and editable 3D images, where you can adjust the different types of threshold pattern of the or density of your digital data and voxels and so on. So you have a lot of alternatives for mimic software, and top 10 alternatives you can see on the screen now. And so we have used a lot of times mimic software to let's begin with how the process has been then to extract the 3D mandible out of the CBCT scan of the patient. So once you got the CBCT scan, you can adjust the threshold level of those pixels which are having a particular density. So if you just adjust the threshold level to only highlight the bone structures, then you can just highlight the bone structures, and then your bone can be actually separated out from those of the lesser threshold value soft tissues and so on, and open spaces. Once your 3D model, the soft tissues are already been enabled because of the adjustments of threshold of the pixel size, or whole of the skull with the mandible has been extracted out. And then you can go and evaluate with the help of another software, where you can actually go on cropping or separating out the whole of the mandible from the skull to extract out only the mandible along with the separated from the skull. And then this can be highlighted, and then you can do another surface smoothing and everything the same way, like you can edit any two-dimensional photograph. Like that, there are softwares which will be editing your three-dimensional structure to make it smooth surfaces and so on and so forth. So once your mandible is in hand on the software, you can see now it has been almost like converted into a smooth surface mandibular model, and you can do a lot of adjustments. You want to do a symmetrical height, symmetrical width, any possibility is possible actually. And then you can see the left side is actual anatomical model with having a surface irregularities, which can easily be smoothened out using different types of softwares. And one of the example of this softwares is Autodesk mesh mixer software. So once your mandible is there, you can adjust your mucosal thickness. You can automatically elevate 2 millimeter of mucosal thickness on the mandible to simulate the mucosal layer, and then you can go for a simulation or designing of your mandible for the implants. So implants, you don't really have to go for having a CBCT scan, because it's not really a anatomical structure, and you can mechanically develop these designs using different design softwares. And one of the example of the design software is like SolidWorks software. There are a few more alternatives to the SolidWorks software based on your availability and the subscription accordingly. So look at this one particular example of an implant with a 12 millimeter of height, and we have evaluated the 4 millimeter height of a locator attachment for the overdenture case. And then we can see even the denture, patient's denture also can be scanned using the intraoral scanner, and then the scanned image of a DICOM file can be imported to the thematic software to make it all mesh works. So you have a mandible obtained from a CBCT, you have a mucosa which is automatically been adapted by a 2 millimeter of layer onto the mandible, and you have a denture from patients which is been obtained from the intraoral scanning of that particular denture, and then that subsequent the 3D model is transferred using the thematic software to develop a surface mesh first. So you can see the model, whole of the surfaces are now divided into tiny triangular shape elements and nodes, and those are basically the finite elements, and there are multiple elements, and whole of this three-dimensional structure later on can be converted from the surface mesh mix to the solid meshwork. Once your whole three-dimensional component of all these three, like for example, if mandible is clear, your mucosa is there, and then your denture is also ready, then you can, all these three segments can be put together to have a intersecting or a complete overdenture component or complete overdenture assembly, I would say. So when you are joining these interfaces, there may be few errors which you may have to physically, or you have to manually do those, remove some of the junctional errors in the nodes and elements, and accordingly you will be having this denture, mucosa, and the mandible all together in one. And then you can also put the implants in the mandible virtually, and whole of this mandibular complex assembly is ready for evaluating and calculating mathematically. So once your volumetric mesh is generated, it can be exported to the ANSYS Workbench software. Is one of the mathematical solution software, and you have another few alternatives for that. So before you really transfer this whole of this anatomical 3D meshwork a model into the space, when you want to put some traces from there to evaluate the stress analysis around the implants and bone. So if you apply the forces from up, the mandible can go down. So you need to have some stopper at the base of the mandible, and that's exactly what is known as a boundary conditions. In three-dimensional spatial relationship, you need to apply a boundary condition to any specific object, and it can be done in a x, y, or z axis, any thing, depending upon your direction of the forces and depending upon how you want to do the testing analysis. So in this particular model, we have a base of the mandible which is cropped straight flat, and then it has been given the boundary condition to be stable at that point, and then whatever forces are applied, the mandible will not move down in the space virtually. And that's exactly what is there. So we have a denture, we have a mucosa, we have a implant, we have a bone, and every component of this overdenture assembly will be having a Young's modulus of elasticity and Poisson's ratio. So these are some properties, physical or mathematical properties, and every property will be having a particular value which you need to incorporate in the software. And once that value is in, for example, if acrylic resin is for the denture, it is Young's modulus is 8.3 gigapascal, and then for the titanium for the implant is 110 Young's modulus. So accordingly, these values, once you put it that for that particular component of overdenture assembly, in three-dimensionally, these structures will act similar to the physical model. So that's exactly what is the idea behind it. So these values are very important, and whenever you want to publish or whenever you want to do this finite element analysis, every structure has these values which you need to put into the software to evaluate or simulate that exact structure in that particular manner. So accordingly, we have force application. You can apply 100 Newton bilaterally, unilaterally. You can increase the force, and based on previous research and based on the amount of forces which are required to develop. And once you can now say that how once your forces are applied, how they are moving. So once you can see the 100 Newton of force is increasing, so then you can find out that the forces are transferring from this molar region to mucosa and then the bone, and then eventually somewhere implants in the anterior zone and so on. So this is how it works basically. So this stress analysis usually can be done in multiple finite element commercial packages. ANSYS is one of the famous software which can be used for these types of works, and then you have few more alternatives like Autodesk and COMSOL and so on. Okay, so once you got these results, you can have a series of color codings onto those implants, onto those structures, and those color codings are actually been given automatic values of von Mises strain gauges or stress values, like there can be they can be presented into Pascal or megapascal values, and then you can also evaluate it in strain values, which can be direct values, which are the change in a dimension upon the original dimension. So stress and strain value both can be calculated in this mathematical software solution softwares, and accordingly the values will be indicating, the more red color will be indicating higher stresses, and as you go lower and lower, the dark blue color will be indicating the lower stresses, and in between the yellow and green colors are appearing. So accordingly you can evaluate, accordingly you can know that, okay, once you apply the force in the molar region, I can see the higher stresses in the molar region. You can separate it out, the mucosal layer, you can separate it out the bone layer, you can separate it out the implant layer, and you can actually connectively also evaluate the stresses, and that's how it works, and it looks like that. So as a clinician, it's interesting to see that okay, the forces are actually going on the posterior side. Why not to just put the implants in a little bit of anterior side to just avoid some more stresses, and that's how the concept of finite element analysis will be helping out. It's not just the modeling of these mandibles is possible only with the help of CBCTs or patients' anatomical data, but you can actually create the mandible physically, and that's also possibility. that once you can do, so this is one example of a physical modeling of the denture, physical modeling of the bone, and physical modeling of the implant. It doesn't have to be uh, anatomical model. However, if you use an anatomical model for the 3D element analysis, that will be very close to the natural conditions, and that's exactly increasing the validation of this in finite element analysis procedure later on. Okay, so to understand a little bit more, again, we have two implants placed in the mandible region, and then you want to test the hypothesis that if I change my position of the implants, if I change my angulation of the implants, if I change my diameter of the implants, how these traces are behaving, how these implants are, how these overdentures are behaving. And if I have to test this hypothesis, probably I have to work around the whole of this, developing the 3D modeling and converting into a mesh model to provide it the solution from the ANSYS software to evaluate the stress and strain analysis. And then once you got one model, you can actually evaluate n number of conditions by changing n number of position of the implant, by changing n number of angulations, by changing n number of diameters and surface topographies of implants, and so on and so forth. So all this can be possible by doing one particular designing, and that's how. So once you look at the change in the implant angulations, you can see that the stresses in the implant are having a little bit of up and down. With increasing in the angulation will be increasing the stresses, and so on. So once you can, so similar studies are also published. We have also managed to publish a few results in the Journal of Prosthetic Dentistry in recent publication, where we have changed the implant angulations for the overdenture attachments, and then overdenture abutments, and then implant placements have been tested with different angulations, and whether the stresses and strain analysis really affect the implant and all. We have also tested the changing the diameter of the implants by placing the implants in the same position, and look at the results. If you increase the diameter of the implants, you are getting the lesser stress concentration into the implants, and so on. So accordingly, we have also evaluated by placing the parallel implants into 5 mm, 10 mm, 15 or 20 mm distance in the mandible, and unilateral or bilateral force was applied in these modeling, and then we have results which are indicating that if you increase the position of the implant from midline, you're getting the higher and higher stresses. So it's understood that once you are applying the force in the molar region, and if you place the implant in the 5 mm position or 10 mm position, they are certainly be a little bit away from the actual more stresses. But as you go closer to the occlusal or loading point, you will be having a higher stresses, and that's exactly what is been observed in the graphical position, and that's how the finite element helps us to understand the stress and stress analysis pattern in these particular scenarios. So you can actually test different graphical presentations in the stresses happening in the mandible, mucosa, overdenture, then implant, and so on. So once you can see that the highest of the stresses are actually observed in the implants in a particular region, lowest stresses are actually observed in the mucosa, of course, because it's a soft portion, and then it is the stresses are easily being dissipated directly to the bone, and probably the mandible will be also having some more stresses more than the mucosa, and that's exactly what has been observed. Even the overdenture has got a higher stresses than the bone, and then the mucosa, and even the implants, and that's how we can analyze and understand this stress analysis around these implants. When you look to standard implants in the position and you change it to the mini implants or lesser diameter implants, you can see now that the forces and then the stress concentration is more into the neck region, and that's exactly where the crestal bone loss is actually happening. So evaluating the stress analysis into the implants and the bone is very important, and that can be only done by the finite element analysis procedures. And I would say that it saves quite a lot of time and resources by using these same test mechanically in the laboratory or clinically in patient's mouth with using a multiple implants and using multiple patients. So that's exactly is the evaluation. So we have also tested the hypothesis with changing the diameter of the implants from standard to the mini implants, and the results have been indicated that the standard implants has a lesser stresses, and then the mini implants, which are having a lesser diameter of implants, are technically having a higher stresses into the overdenture pattern. So probably mini implants are not really a great option to indicate or go for the two implanted and overdenture. So these types of problems can be solved easily using these finite element analysis results, and that's exactly what we can achieve with the help of this method. Okay, so clinically you can validate. Clinically you can actually use it. For example, if you have a lesser diameter of implants, you can have a higher stress concentration, and it can be also been transferred and analyzed that, okay, because of the lesser diameter, because of the lesser surface area, your pressure and force is going to be more onto the mini implants as compared with the standard implants, and that exactly which we can we can evaluate accordingly, and so on. So clinically also you can correlate these findings. However, there are multiple influencing factors which you also may need to consider. So once you have done a finite element analysis, there is a very important factor left behind, is called as a verification or validation of the process. In clinical practice, you may develop a very nice three-dimensional model with a very good finite element analysis, but clinically, if you cannot correlate the values with the clinical results or mechanical models, then there is no point doing the finite element analysis and so on. So verification is something which is, there are the two ways. One is verification of finite element method, and another is validation. So prediction and confirmation of the physics appear in the verification and validation respectively. So prediction becomes verification, confirmation becomes validation. That means verification means if you do a finite element analysis and you have a similar types of forces are being discovered or presented with in line with your previous studies or in line with your standard of observations, then your values are verified. Validation is something like you have done the finite element analysis and then you want to validate these results with the using the mechanical models or using the clinical models or in clinical patients. So whether you can correlate the finite element analysis results with the mechanical studies or physical models, if they can be correlated, then the results are validated. Accordingly, you can test. So there is a very good a flow chart given by the American Society of Mechanical Engineers to understand what do you mean by verification, what do you mean by validation. So once you have an anatomical model, mathematical, you want to do the stress analysis, there is one way is your software way, is a finite element way, is a mathematical model, and another way is a physical model where you have to print, you have to develop physical models, and then you actually do the stress analysis using strain gauges or whatever in a universal testing machine and so on. So that's how. So one is a virtual modeling, one is a physical modeling. So virtual modeling is all about finite element analysis, where you have to develop the mathematical model, and this mathematical model, if you are giving a similar types of results with the previous standard results, then yes, it is verified. Once you have done the finite element analysis, and then if you the similar results are obtained or you can correlate with the physical or experimental models, then these results are validated. That's exactly how you need to understand the finite element analysis workflow. Yeah, so there is a workflow pyramid where, so how to minimize these errors or how to enhance the validity of the finite element analysis technically. So when you do a simulation, try to do a separate analysis of different components. For example, you do a separate analysis on the bone, the mucosa and the denture, and then the standard implants or mini implants, and then you try to individually prepare or fabricate the individual geometric model to make a complex component or overdenture assembly. And that's how slowly once you are pretty much sure that okay, my individual models are working well. Whenever I'm applying some certain degree of pressure, it is giving you a similar values like previously or something like a, they are also, I can validate with the physical models. Yes, then you can make the whole junctional nodes to make a complex component or addition or combination of all these into one complex design, which is a overdenture assembly, where you can evaluate the whole of the stresses in any part of this assembly. And that's how. So 3D modeling, you can do a validation by using the same 3D model by 3D printing, using the 3D printing. And then once your model is ready, you can just put the anatomical or physical implants in the mouth, in the models, and then your even the denture can be scanned, and the still file can be actually 3D printed to make a duplicate dentures. And once your denture, you can put the physical implant in the model, you have a physical locator attachment, you have a physical denture, you make a mucosal layer, you attach the overdenture attachment, and then do the testing. So this is like a physical modeling, physical testing, which is using the different strain gauges. So these strain gauges are attached to the model. For example, these are the strain gauges, some very tiny strain gauges. You need to stick it to the models, and then this eventually will be calculated with the help of strain evaluated software and strain gauge softwares, and accordingly you can evaluate. So the stresses can be applied on a unilaterally, stresses can be applied on a bilaterally, and accordingly you can evaluate all these strain gauges and validate your results outside in the finite element analysis. So to have some clinical judgment around these studies, I would rather again use the simple example of using the position of implants. There is one study where they have concluded that the canine position is preferred over the first premolar position for the two implanted and overdentures. As you go posteriorly, they have observed more crestal bone loss in 1 year of a recall appointment. And then you can correlate the results like, okay, in finite element analysis also, we have observed that if you place an implant in a 20 millimeter position, you have a higher stresses. As compared with the implant in a 5 or 10 millimeter position, you will be having a lower stresses. So that's how the clinically also you can have judgment that, okay, more placement of implants may have a higher stresses profile. That could be one of the reasons that you can get a extra or additional crestal bone loss, and accordingly. So even with same goes with the implant angulations. The angulation can be a buccolingual angulation, can be a different angulation with the occlusal plane, or angulation can be with each other for the two implants, and so on. So all these angulations are also been very complex, and then you cannot really validate. And if you have observed the stresses or additional crestal bone loss on the more angulated implants, and if you have a stress analysis done in a finite element analysis, also indicating that more angulation of the implants, more will be the stress concentration around those implants, and then you clinically judge that, yes, I would say rather. But is this the clinically validation is true? Is it real validation? Why only the stresses at the crestal bone of the implants may cause crestal bone loss? Is this the only reason? If you have a higher stresses around the crestal bone region or crestal region of the implants, and that is the only reason? Probably no. There are multiple confounding factors. There are multiple influencing factors which may also come into a picture, and that's where exactly we can coin the term called as a validation uncertainty. If you don't have a certainty that higher stresses probably not only the reason for crestal bone loss, or that particular reason probably could be because of a patient's systematic condition, could be because of a patient's infection control, because of the maintenance, because of the many masticatory efficiency or chewing pattern, or eating a type of a food, or so there are so many subjective elements which come into a picture to allow that that you may have validated. So that's exactly is you may find some validation uncertainty in especially in a complex clinical situations to evaluate, and that's exactly where you. But still, finite element analysis will still give you some guideline to evaluate the bone loss. So there are multiple confounding factors which come into picture, as I earlier discussed about like, for example, a bone quality or quantity, type of implants, size of the implants, type of attachments, occlusal pattern, chewing habits, denture basis or teeth materials, mucosal thickness, patient systemic condition, and so on. So all these factors may influence your stresses. So stress analysis could not be the only factor which may happen to occur into the, but certainly it could be one of the important factors that higher stresses may cause some bone loss and so on. So what we are taking, so I am stopping here now with the take-home message that finite element analysis is a useful and a smart research tool in implant dentistry to evaluate stresses and strain values, and can be correlate mechanical and clinically as well. Finite element analysis helps saving hardware resources and time. And however, the validation of this method or results for the complex anatomical structures must be done carefully, especially when you want to read this in a clinical scenario. With this, I would rather say thank you so much. Most of this work I have learned a lot from my colleagues, Dr. Piyush and Dr. Rashmi from Nagpur, from India, where the Regional Engineering College has helped me a lot to understand this methodology, and a lot of research has been done with this collaboration with this institution. These are some of my key collaborators with one of my supervisors and so on. With this, I stop here to announce that we are running a small one-year diploma program in prosthodontics in International Medical University here with the 30 credits. It goes along for the whole one whole year. With this, thank you so much, Dr. Mohammad Al-Basti, for giving me a wonderful opportunity to speak in front of this wonderful Digital International Academy, Digitodontics International Academy. Thank you, one and all.
Thank you so much, Dr. Patil. It was really inspiring lectures. I really like it because you took us to the many important aspects in the field of the finite element analysis. So you dived us to the literature that related to this field. Then you explained to us the how this approach is possible with different techniques and ways, and then you applied those techniques on the clinical situations. And we can see that it's very important to decide where you put your implants, what kind of implants that you need, and everything. So it's really inspiring us, and very informative lecture that you presented. So once again, for the attendees, if you have any questions, so please write them on the Q&A, and Dr. Patil will answer them. Dr. Patil, just I have a question. So you mentioned that either to simulate the anatomical model through the CBCT and DICOM data, or even you can create your model, visually with the software. So what kind of challenges that you face when you apply such approach to analyze the stress for the implants and the components in the finite element analysis?
Yeah. Thank you so much for the question. Yes, it's a valid one that you can go creating any three-dimensional structure. Yeah, the complexity, the difficulties are in both ways. One is, if you want to go without an anatomical model, you have to create one. And no matter how you create a physical model, it cannot be simulated as an anatomical model. So you need a lot of design expertise in that particular, specifically if you really want to design everything digitally in the software. The anatomical model is next to impossible, and it's very difficult to achieve that high degree of this designing characteristics. However, you can definitely smartly design similar looking physical models like a U shape, convexity, and so on and so forth. Uh, the other way around now, for the anatomical models, difficulty is to have scan, and then you can use the mimic software to extract out the anatomical structures, and you want to do some of the adjustments in the models, and but that is also still fine. What is more complex in the anatomical structure is the stress analysis. So every mandible, probably the angulation, even the in the anatomical structure, even the incline of the anterior portion, incline of the posterior mandibular portion, the amount of cortical thickness, amount of medullary thickness, lots of complexities are still there which are unsolved, and that could be one of the reason you may not get the similar results for person who is designing or having an anatomical model in Kuala Lumpur, and probably the similar way you want to go and extract and design another anatomical model in Paris, probably you may have a certain degree of variations, and that could be influencing the results at all. However, having said that, the engineering concept saying that as you go, the validation concept says that whenever possible, you want to go very close to the anatomical structures to simulate very closely, so that you can have more valid results, and you probably having a easier task to validate the finite element analysis. I have answered your question.
Yeah, thank you so much. So I think we have one question here from Dr. Zhao. And I think he asked about the software ANSYS.
ANSYS, yes.
Yeah, and also the Abacus as well.
Yeah.
Yeah. So I'm not sure what he exactly mean by that.
Yeah, probably Dr. Zhao wanted to say whether it's the same software. Yes, it's definitely is the same software which is used for the utilization in the mathematical solutions. Abacus, however, I am not sure really, but I can say, let me just go to the one of the slide where I have written few of these. So I think there are multiple softwares available which are helping to evaluate the mathematical solutions, and probably I'm not sure about the Abacus, but alternatives to the ANSYS software are like Autodesk, then ComSol, then MS Nestran, and then Opera, and so on and so forth. Yes.
Yeah, so maybe Dr. Zhao, if you can explain more what you are asking for exactly. So yeah, so I guess he thanks us.
He
so
got it. Yeah.
I think we answered his question. So good. I have another question, Dr. Patil. I will shift you a little bit to the a part of prosthodontics, which is the maxillofacial prosthetics.
Yeah.
You know that we are using zygomatic implants, and that's an advantage for the oncological patients. Have you applied the Phenol element analysis on zygomatic implants, especially that it has different angulations, the length of the implant, the dimensions, and everything. So have you have that experience, please?
Well, yeah. Unfortunately, no, I would say. But it's interesting that I have gone through a couple of cases or studies where they have tested already the stress analysis around the zygomatic implants. The interesting part about the zygomatic part of the implant is outside the bone, and part of the implant is inside, and then probably sometimes it's the end is only in the inside the bone. And then that's exactly is variation where how many millimeters of implant has to be outside, and in every case varies, and that's where probably the few results may vary from patient to patient. And but yes, certainly whenever it's possible, it is definitely possible. One of our paper in recently last year published in Journal of Prostate Dentistry, where the obturator, we have designed the obturator using the full digital workflow, but Yeah, and then evaluated the stress analysis around those areas, how we have a masticatory after the occlusion or masticatory forces, how these stresses are going in which areas or which part of the stresses. Yeah, but zygomatic implants, I would say, is more or less this is a matter of study. It's just that you just have to follow the few given principles by the already researchers has suggested. If you have some variation, you can always use the finite element analysis to suggest some better versions of those. Yes, for sure.
Yeah, thank you so much. So I'm not sure if you still have time. I have a couple of questions from my side. You know that using many softwares is kind of expensive approach, and sometimes funding for research is a big challenge. So how can you manage to apply all these kind of analysis and softwares when you have a limited fund resource?
Yeah, smart question, meaning I would say is all about networking. And if you really have you just have to find the key resource persons and few people who are really closely working with you, and they follow your own philosophies and work together. Fortunately, I'm lucky to have one of the good understanding people who are working more. Those are engineers. They are mechanical engineers, understanding the dentistry point of view, some of the components, and they have worked together with us. And so how we work here about the research, of course, definitely funding is a very challenging task. And if you can find out people who are working already in an engineering college, they must be definitely having the subscriptions of these higher softwares. For example, in my case, ANSYS software is not really cheap. Subscription is very high at rate, and you cannot really technically use anything, and you can't even use the technique expertise as well. So if you can just collaborate with the engineering college where you can have these facilities, you have a expertise and person, and then what is a missing link is that you need to just approach for those, you need to identify those people who can do more of this complex task. Having said that, all the software subscriptions also will be there, and then you just have to prepare your proposal. Of course, you can negotiate some amount of these rentals and some amount of your software, and I'm sure that there are quite many institutions, especially I know in India, will be happy to do this job with a very substantial and good price, if you're really asking about that aspect. And funding probably is not that much of an issue. Whatever you can see, some of my research projects which have been done in a very reasonable funding resources, as long as rentals and the subscription is concerned from that team. So in and all, it's just networking issue, and you really have any person who is really keen to do that, I'm happy to collaborate, and we can do grow together.
Yeah, I totally agree with that, especially that when you collaborate, especially with the engineering colleagues, because we still have the issue that we don't really have that deeper background of the engineering behind the softwares and the analysis and stuff like that. So collaborate with the engineering and technical colleagues will highly improve the approach and using the techniques and softwares and everything. So I totally agree with that. So last but not least, in a few weeks, we do have a lecture or two about the artificial intelligence. And I would like to ask, what is the role of artificial intelligence in finite element analysis?
Yeah, probably, yeah, it's a matter of time, and artificial intelligence is going everywhere. Why not in finite? Is really actually very close to, these two are very close. why not? Like artificial intelligence is actually going into how to select the restoration material, how to select your prosthetic design, how to select everything. They are, you just have to key in thousands and thousands of clinical situations in that, and they are just selecting and giving you a right choice. Finite element analysis, probably I can foresee that it's even easier for them to just analyze and give the final results, and it's almost really closer to, I would say, I'm not an artificial intelligence guy, but I would say some interesting things there, and yeah, anything, yeah, it's just a matter of time.
Yeah, I think it's because the analysis is mainly depend on the numerical
Numerically, yep,
data, and
yep,
artificial intelligence is based on how to train the data
the data,
and the model to be follow the numbers and everything. So I think it's very
perfect.
close
Yeah,
the finite
sounds good. Yeah, it's a good
analysis.
idea.
Yeah,
It's a good
yeah,
idea.
exactly.
Now,
So
something is cooking
yeah,
in mind now. Yeah.
yeah, yeah. I think this kind of webinars is open doors, for many colleagues to collaborate
Yeah.
and do many things. Even myself, I'm highly interested to test the Zygomatic implants, for example,
Oh,
the stress and everything. So that's
okay.
why I ask this. It's very,
Hmm.
very important, I think. So I think with that, we came to the conclusion of our webinar for today. But before to close the session, it's the Digitodontics tradition that present a certification of appreciation. So we hereby express our sincere appreciation to Dr. Pravinkumar Patil in recognition of his contribution as a live webinar speaker for the Digitodontics Webinar Series on the topic of the finite element analysis as a smart implant research tool that was presented on Tuesday, September 13, 2022. So, Dr. Patil, I
It's been,
really thank you for your time and opportunity for presenting us with this very valuable webinar that I'm sure that all the attendees and later who will watch it on the recorded version will get the benefit of it. So thank you so much.
thank you so much for the opportunity, and yeah, all the best for future webinars, and hope to see you soon. Thank you so much, Dr. Mohammed.
Thank you.
Yeah, yeah,
Have a
it's been
nice
an
evening.
honor. It's been an
Yeah,
honor to be here. Thank you so much.
thank you. Bye-bye.
Thank you. Bye bye. Take care.